Hello and welcome. In this tutorial, we will evaluate a trained deep learning-based classification model. Evaluation in this context means that we check the performance of a model on independent data, the test split of our dataset. Thus, we make sure that the model is good enough to be deployed. For this video, I adapted the third example in this series on HALCON classification. In the example, you can use either a model that was pre-trained by MV-Tech or a model you trained yourself, usually with the previous example. For this video, we use a model from a training with only one epoch that doesn't perform very well. The example basically executes the procedure evaluate DL model and visualizes the result. First, we visualize various results with dev display classification evaluation. Let's have a look at the confusion matrix. With this matrix, you can compare the ground truth labels with the predicted classes. Ideally, you would have all the instances on the green diagonal where the ground truth matches the inferred prediction. In this area, you see any instances that are classified incorrectly. At the top left, we see some pie charts for the precision of all classes and the individual classes. A high precision means that when the model assigns an image a certain class, we can be reasonably sure that the label was identical. Here, in particular, the class good has a rather bad precision. This is because some images that were classified as good were actually cracked or contaminated. This is also called a false positive. Below this, the recall is visualized. By contrast, this value reveals images that were labeled with a certain class, but then classified differently by the model. A problem this model seems to have is that images that are labeled crack are then often classified as good. This is also called a false negative. Both values give you a good impression of the performance of the model. However, one or the other might be much more important for your classification problem. Additionally, the F-score is the harmonic mean of both values. You can also inspect the underlying images using the interactive confusion matrix. Clicking on the elements of the matrix shows the respective images, their ground truth label, and assigned class. Next, HALCON offers a heat map that can give you some more insights into your model. The heat map highlights the areas of the image that influence the classification decision the most. Thus, it can be useful for checking the inner workings of your deep learning model. It can help assess whether the model learned generic features, or rather unexpected or unwanted information. Also note the procedure find DL samples. This procedure can be used to filter samples. For example, you can retrieve samples according to their image ID, or from a certain split. Additionally, this procedure can be helpful if you organized your dataset with custom keys, for example, the camera setup with which the sample was created. Last in this example, we execute setDLModelParam with the parameter optimize for inference. This reduces the memory required by the model by deleting data which is not necessary for inference. This concludes this video. Now, when the evaluation is satisfactory, we only have to deploy the inference, which we will learn about in the last tutorial of this series. Thank you for watching.